In this video, we are going to talk about non-parametric distributions, which are essential to the particle filter algorithm. But in order to speak about non-parametric distributions, one needs to explain what parametric distributions are. And to do this, we need to go back to our sweetheart, the Gaussian distribution. Now, the Gaussian distribution can be described by two parameters and two parameters only, mu and sigma. And if I have those two parameters, I can A, draw this function, and B, compute it at any point. And this is what makes the Gaussian distribution so strong and so useful. You only need two parameters and you can know anything there is to know about the Gaussian distribution. But what happens if you don't have this lovely, beautiful function? What happens if you have an arbitrary, nonlinear, multimodal distribution? You can try to find the mathematical function of this distribution, but this could be challenging, especially if you are talking about multiple dimensions. But there is another way. You can describe this distribution with points. Let me demonstrate. Take this point, for example. At this point, the probability is high. Therefore, we will draw a large circle. On the other hand, at this point, the probability is low. So we will draw a tiny circle. And over there again. And now it's a little bit bigger. Now it's a little bit bigger. But then it transformed to be much bigger. So you can draw a circle that represents the probability at any point. And just by looking at the circles, at their size, one can determine what the initial distribution looks like. The first one is a Gaussian distribution. And the lines that you see here represent sample. Okay? And the lines that you see here represent samples. When I draw samples from a Gaussian distribution, I will get a few samples over there and a few samples over there, but at the mean, I will get a lot of samples, a lot of lines. Now, you can do exactly the same thing with an arbitrary distribution. Now here you see, when the probability is low, we will get a few samples over there and over there. But here, when the probability is high, we will get many samples. Again, over there, it's a little bit lower, so we'll get less samples than over there. Okay? And again, one can describe this function with lines or points. And this is exactly what non-parametric distributions are. You can determine or you can describe a function using points or lines. Let's go in more detail. A particle set is a set of weighted samples. Each sample holds the state hypothesis and the importance weight. You can think of the state hypothesis just as a state vector. This is what your belief about the robot is, where the robot is in 1 dimension, 2 dimensions, or 3 dimensions. And the importance weight is a factor of how probable that belief is. For example, if the belief that the robot is at x equals 15 is larger than the belief that the robot is at x equals 8, then the W, the weight of x equals 15, will be larger than W of x equals 8. The importance weight is an indication of what? Of our belief, of our probability in that specific state. Now, if you remember, the delta function equals 0 everywhere except for at x equals 0. Okay? Over there, what I have is sigma from j equals 1 to capital J, omega j times lambda xj x. And what I get is like a set of pointed arrows, okay? Each arrow with a size of W. This is W1, W2, W3, W4, etc., etc., etc. And if I have enough of those arrows, I can describe the initial arbitrary distribution. And this is, I think, the most important thing about particle filter. One can determine the nonlinear arbitrary function from its particles, from its point. Each point is called a particle. And this is why it's so important, because we are not restricted to a Gaussian parametric distribution. We can work with any kind of function. This is what makes the particle filter so strong when it comes to self-driving cars. And the best part is that it is the easiest to program.